That jumped ahead. Thanks for the introduction, Anna. And good afternoon, everyone. So my name's Katherine, and I'm a Royal Academy of Engineering Research Fellow at the University of Southampton. And this presentation is going to be about mooring and anchoring systems for floating offshore renewable energy, mainly looking at the seabed and embedded chain anchor interactions and optimizations in sand. So the catenary mooring line configuration is quite a common mooring system that is used to hold floating offshore infrastructure in place. And in particular, the embedded mooring line section is an integral part of anchor design because the formation of its inverse catenary shape affects the loading that is resisted by the mooring line, as well as the magnitude and the direction of the load that is then transferred to the anchor pad-eye point. Now, there are analytical chain equilibrium equations that describe the forces around each individual element of chain and can be used to calculate the load displacement response, as well as the shape of the inverse catenary chain profile as the chain is tensioned. Now, in fine-grained soils like clay, the sliding and normal resistances in these equations are quite well defined. They're a function of the undrained strength of the clay as well as the bearing capacity factor. But in coarse-grained soils like sand, the parameters for the sliding and normal resistances aren't so well defined. So the aim of this work is to investigate the combined embedded mooring line anchor system capacity in sands, and to also identify the effects of mooring line thickness and sand density on the combined mooring line anchor system capacity. So we developed some centrifuge tests, and you can see the experimental setup here of the strongbox, which allowed us to apply tension to the chain at the sand surface or the sea floor, and then we were then able to measure the resulting displacement as well as the magnitude and direction of the resultant loads that are then transferred to the anchor pad-eye point. And we did that by resolving the horizontal and the vertical forces that are measured by two orthogonal load cells that are attached to the base of the strongbox. What we could also do was measure the chain inverse catenary profile by very carefully probing along the length of the chain. And we tested two chains, a thick and a thin chain, embedded in a dense and a loose sand. So now for some typical results. So what you can see here is a tension displacement response of the chain as it is tensioned. And you can see that it's highly nonlinear. So there is a rapid increase in the tangent stiffness as the chain is tensioned. Now what we can also do is normalize these loads to look at the load transfer or the load proportions that are transferred between what we apply to the chain at the sand surface to those that are actually applied and transferred to the anchor pad-eye point. And what you can see from these results is that initially the loading at the pad-eye point is quite vertically orientated, but as the chain is tensioned, cuts into the sand, a higher horizontal component then develops. You can also see the unloading-reloading loops in the data, and that's just from us spinning down the centrifuge to then measure the chain catenary profile. If we look a little bit closer at the horizontal and vertical tension components at the pad-eye point, what you can see here is that, again, the tension at the anchor pad-eye point is initially quite vertical, which is consistent with the initial shape of the chain. But as we tension the chain and it cuts into the sand, the resultant force at the pad-eye point then rotates around as an inverse catenary shape forms in the chain. And we can draw a load vector, like you can see here, which defines the magnitude as well as the direction of the load that is at the pad-eye point. What you can also see from this data is that thinner chains cut more into the sand than the thicker chain did, thus developing a higher magnitude of tension, as well as a flatter loading angle at the pad-eye point. What you can also see from this data is that both the thick and thin chains cut more into the loose sand than the dense sand. So if we were to imagine or add or define a typical anchor failure envelope, like for a suction caisson, then what this data shows is that, well, we can define a combined mooring line system anchor capacity by looking at the intersection of the load vector with the anchor envelope. And what you can see here is that the thin chain, in this case, cut more into the loose sand, thus mobilizing more horizontal anchor capacity, and so higher combined mooring line anchor system capacity. So, analytical chain equilibrium equations do exist to describe the embedded chain response, And in sands, we can relate the normal and the sliding resistance to the cone penetrometer tip resistance, as you can see defined in these equations here. But what we found was that we weren't fully able to replicate the centrifuge results that we measured by using this formulation here. So we developed a new formulation where we introduced the dependency with the normal and the sliding resistance of each chain element to the local chain element angle. And you can see the formulation here. So what this means is that if we had a horizontally oriented chain element, then the normal pressure acting on that is equal to a factor of the cone penetrometer tip resistance. If we have a vertically oriented chain element, then the normal pressure acting on that is equal to a factor of the limiting lateral stress, as if the chain element were like a laterally loaded pile. And the way that the normal pressure varies with the local chain element angle varies with an exponential trend, which is consistent with stress rotation theory, so the change in mean stress through rotation of principal stress direction in frictional materials. So you can read more about our new formulation as well as its validation with the centrifuge results in a paper here, which was recently published in Geotechnique. So we can use this new formulation to then investigate the combined mooring line and anchor system capacity for a range of different chain thicknesses in a dense and a loose sand. And if we have a look at the combined mooring line anchor system capacity, what you can see here is that for chains which were thinner than an effective mooring diameter of 500 millimeters, that their combined capacity exceeded what you would get in a dense sand and a loose sand, even though the anchor failure envelope is actually smaller in a loose sand. And the reason for this is because the reduction in anchor capacity in loose sands is eclipsed by the increase in tension that you can get from thinner chains cutting into looser sands, thus mobilizing a lower inclination angle of loading. And again, just for this case, if we now compare a thin and a thick chain, where the thin chain is half the diameter of the thick chain, we could get up to a 34% increase in the combined chain anchor system capacity. And for this thin chain, we could get up to a 27% increase in the combined capacity if it were in a loose sand. And if we were to imagine or model a novel synthetic fiber rope with some sheathing that we've also sized to have the same or comparable minimum breaking strength to the thick chain, we could get potentially up to a 40% increase in the combined mooring line anchor system capacity. So, in conclusion, we have investigated the combined embedded mooring line anchor system capacity in sands for a range of different mooring line thicknesses and sand densities. And what we can see here from these results is that there are cases where a thinner chain can cut more into looser sands, thus mobilizing higher combined system capacity, which highlights the importance in needing to size both the anchor and the mooring line components together to find an optimal solution. And the model that we have for sand provides us with a simple tool that allows us to assess and quantify this interaction. Special thanks as well to co-authors of the conference paper and also colleagues, Colmore Byrne, Joe Q, Dave White, Conleth O'Luan. So thank you for listening and happy to answer any questions a bit later.